as we're getting ready to start here, I want you to think about your objectives for today. So along with the 2 agree-disagree statements from your bell ringer, you also should be thinking about what you are intended to learn today, which is you're going to be able to describe and apply the law of conservation of energy. So you're going to be able to describe means tell me what it is, and apply means if I give you a situation, you will tell me how it affects that situation. Then you'll be able to explain how energy can be transferred and how it can be transformed. So you'll need to be able to do both of those things. And you'll be able to explain how work and energy are related or connected to each other. Those are our goals for today. So we'll just launch right in and start talking about energy transformations. We discussed this a little bit in the previous lesson. We're just going to talk about it a little bit more here. Okay, this is when we change from one type of energy to another type of energy. You had a few examples of this in the past chapter or past lesson. Here are a few more. Okay, roller coasters. Roller coasters are really good situations to explain kinetic and potential energy being changed back and forth. So you start with potential energy at the top of a hill, it becomes kinetic energy as you move down, and then as the object moves back up the hill, it slows down, losing kinetic energy, which is being transferred into potential energy again. Plants take radiant energy from the sun, which is light energy, and they use a process called photosynthesis to change that into chemical energy that then they store in them. So all plants have chemical energy stored in them. Even tree trunks and carrots. Okay, so if you were going to release the energy from a carrot, you would eat it and digest it and break it down and release that energy. If you were going to get energy out of a piece of wood from a tree, you'd have to burn it. But they have chemical energy stored in them. Okay, and then one that we don't often think about is fossil fuels. Fossil fuels are formed from the remains of once living organisms that have been buried, and then over time, pressure and heat from the earth can help to change those into fossil fuels like oil, natural gas, and coal, which still have the chemical energy of the plants that they were made out of. Now, when we burn those, then we get thermal energy. Now let's talk about energy that's just transferred, because this isn't the same as being transformed. When energy is transferred, it's just passed from object to object. It's not changed. The type of energy doesn't change. So think about if you have a heat lamp. That thermal energy produced by the lamp can pass from the air, through the air, and to another object, right? So it may heat the air, and then that air can heat, say you have some chicks sitting under your heat lamp. That energy didn't change form. It's still thermal energy by the time it gets to the chicks. It's just being transferred from object to object. Another good one to think about is if you swing a bat, that bat has kinetic energy because of its motion, right? And if you hit a baseball with it, that baseball is going to get that kinetic energy and it's going to move. So still kinetic energy, it's just been transferred from one object to another. It's important to remember in both these situations that energy is conserved. This is such a universal fact that we have found to be true over and over and over again that it's now considered a law. Okay, the law of conservation of energy says energy can be transformed from one form to another, but it can't be created or destroyed. You're not going to make any new energy. You're not going to destroy any energy that already exists. The type of energy can change, the object that the energy is in can change, but the total amount of energy will not change. It will be the same at the beginning and at the end. Now let's talk about work, because that's a new concept from this section. Okay? Work is the transfer of energy that occurs when a force makes an object move in the direction of the force while the force acts on the object. That's a lot of words all strung together, so I'm going to try and summarize it for you a little more easily to understand. Okay? Work is only done when the following three things all happen. A force acts on an object. The object then moves, and that object's movement happens in the direction of the force while that force is still acting on it. So, think about if I'm holding this jug of hand sanitizer, okay? If I'm just standing here holding it, am I applying a force to it?
Yeah.
Yes. Is the object moving?
No.
No. So that would mean in this case, no work is being done because the object is not moving. Okay? If I push on the hand sanitizer and for some reason it moves in the opposite direction, that means that while work may be being done on this object, I am not the one doing the work. Because if I was the one doing the work, the object would move, but it would move in the direction that I am pushing. So if I am the one to be doing the work on this object, it has to move, and it has to move in the direction I push on it while I am pushing on it. Again, if I push on it, and nothing happens, and then I walk away, and then it rolls off the desk, I am not the one who did the work on that object because it moved when I was no longer applying a force to it. So if I hit a baseball with a bat, I apply force to it, and it moves in the direction of the force. So work is done. However, as soon as I stop applying force to that ball, even if it continues to move, I am not doing more work on it because I am no longer applying the force, so I am not doing work. I'm only doing work when I'm pushing on an object with a force or pulling on an object with a force, and that object moves in the direction that I apply the force in while I'm applying the force.
I took an hour nap in the car.
Work always causes a transfer of energy. So if you're following along with the objectives and you're trying to find the connection between the two, when work is done, energy is transferred. That is our relationship between them. Anytime that you do work, energy is being transferred. How much work is done is going to depend on a couple of things. First, it will depend on the amount of force that is used to move the object. So a stronger force equals more work done. And it will depend on the distance that the object moves. So if the object moves a larger distance, then more work is done. You can use the following formula to calculate when work is done on an object. Work is equal to force times distance. In this situation, when we say force, we mean the force applied to the object, not just any random force. And when we say distance, we mean the distance that the object moves while the force is being applied. Units for work are measured in joules. Joules, spelled Joules. Okay. Force, as you remember, is measured in newtons, and distance, as you will hopefully remember, is measured in meters. So, because work is equal to force times distance, work is measured in newtons times meters, which we know as joules. So a newton meter is a joule. That's the name we've given to that calculated unit. So you can either write the full word or you can write the letter J as your unit. The last little piece that I want to talk about is the relationship between energy and heat. Okay? Because you may have heard of people talking about losing heat or losing energy to heat. So what's happening there is that anytime the energy is transformed or transferred, some of that energy is changed to thermal energy. And that thermal energy moves from areas of high energy or high temperature to low energy, which is low temperature, and that flow of energy from high to low is called heat. So when you put your hand on the cold desk and you feel thermal energy travel from your hand to the desk, we describe that as heat moving from your hand to the desk. Okay? Because Heat is often called waste energy, or it's often called being lost as heat. This happens because thermal energy is not easily used to do useful work. Okay? There are some situations where you might use heat to make steam to power a generator, but in everyday situations, like when friction causes me to change some of my kinetic energy into heat energy, I can't easily trap that heat energy and use it for useful work. So, because it's being converted to a form where it is not easily used by me and it's not super useful to me, we say it's lost or waste energy. It's never gone. We know because of the law of conservation of energy that we don't destroy it. It's just been changed to a form that is less useful to us. That is where our notes end for today.